All right, back to lecture 2 here. Got some new technology, a better document camera. I think that's going to work well. So last class we were talking about what it is to be a fluid, and we said that a definition of the fluid was that a fluid will deform permanently when subject to any shear stress, no matter how small. And we compared that to solids, and solids do deform when subject to shear stress. They will, essentially, they will deform to oppose the force. But then when that shear stress is removed, they will return to their original shape. And unless the stress becomes high enough that you actually permanently deform the solid or break it. But under light shear stresses, they do not deform permanently. They only deform temporarily, whereas fluids deform permanently. And the reason for that is because the intermolecular structure of fluids is fundamentally different than that for solids. So solids, the molecules are actually molecularly bound to each other. The molecules have permanent neighbors. There is some intermolecular motion within the solid, but largely, molecules have permanent partners to which they are bound. In fluids, that's not the case. The the molecules are constantly changing partners. They're constantly moving around, and so they deform, under any shear stress because there's a lot of intermolecular motion. There are two types of fluids. You're familiar with both of them. Liquids and gases are both fluids. So they're very different from each other, but they're both fluids because, as we said, the molecules in those substances do not have permanent neighbors, and they are constantly moving around. And we'll get into a little more about that in a minute in terms of talking about how liquids and gases are different. But here are some examples of fluids, and most of these fluids you're very, very familiar with. So the ones you'll almost certainly work the most with in your work lives are water and air. So they're around a lot, and a lot of people have to work with those, and those are both fluids. Oil is a fluid. Molten metal is a fluid. So when metal's in a solid state, of course, it is a solid, and the molecules are bound to each other in a rigid lattice. But as you melt metal, what that means is you turn it into a liquid state, and then it becomes a fluid because those molecules, those intermolecular bonds are broken by the high energy of the high temp. And so those molecules are free to move around and change partners. And when they do that, they become liquids. An example of a molten metal that you can see at room temperature is liquid mercury. So it just happens to be a metal that is molten at room temps. So you can see a liquid metal in action without getting it really hot. Another example of a liquid is liquid nitrogen. So nitrogen is the primary component of air, but if you cool it down enough, it will coalesce into a liquid, and liquid nitrogen is also a liquid. And of course, nitrogen gas, and all gases are liquids, but just put it down here to contrast it with nitrogen liquid. So nitrogen gas and all the other gases, CO2, oxygen gas, all those gases behave as fluids. Sorry, not liquids, they're fluids. So all of these things are fluids. They are all fluids because they do not withstand any small amount of shear stress. So let's talk a little bit about the difference between liquids and gases. Gases versus liquids here. So we're going to do that. Just get a piece of paper. So gases versus liquids. And in order to consider the difference, I want to imagine two containers. So we're going to have two containers. It's going to be container 1. It's going to be container 2. They're identical containers. They are both rigid containers, rigid sealed containers, and they both have a volume of 1/2 of a meter. So the volume for each one is going to be 0.5 cubic meters. So these are solid boxes. Think of the cubic boxes with fixed volumes. And what I want you to think about now is putting a gas into one. So we're going to have container 1 is going to have a gas. Container 1 contains 1.5 kilograms of air, which is definitely a gas, at the temperature I'm going to specify, T equals 20 degrees Celsius. So at T equals 20 degrees Celsius, you know that air is a gas, and it's in that box. So, let's see what happens there, and then you're going to compare that to container 2, which is going to contain water, and it's going to contain 1.5 kilograms of water. And that's also going to be at 20 degrees Celsius. So you're going to consider both of those. So what I want you to do for this exercise is I want you to find the pressure at the top and bottom of the container, of each container, of the containers. And you can assume that gravity is 9.81 meters per second squared, planet Earth. So there's your task. So what I want you to do now is I want you to turn off the video. I want you to look at these two problems. You have some familiarity with gases and liquids from thermodynamics class and possibly from chemistry. So you should be able to tell me what is the pressure inside container 1. Is the pressure different at the top and the bottom of that box? What is the pressure inside container 2? And is the pressure difference at the top and the bottom of the box? And any other details you can provide me with what's going on there. So turn off the video, give that problem a try, and turn on the video again, the next video, and see what the answer is. Thanks, bye.